My name is James Black, and today I'm going to be talking about how to decompose monoliths. So let's start off with, generally when we learn a new language, a new framework, pretty much anything, the first thing that we do is we tend to go to GitHub and look for sample applications. This makes it easier because the thought is if this company came out with this approach, it's probably what they expect to be the correct approach. So we tend to borrow from them. So for example, there's a pet clinic that is very common in spring. And if you look at, this was a couple of years ago, this one, but if you look at the basic design, you can see that there's various controllers, which will be how the clients will connect to the system. Then you have a service that is actually where it seems to have all the core business logic centralized there. And then you have code that goes out to the different databases. So most likely this is in this case it's set up for one database. They either use HSQL, or which is an in-memory database, or they use MySQL. So this looks like a fairly common approach that people have. When you start to look at this and you say, okay, this looks like good design, you run into problems early on where if I'm trying to have REST calls coming in, for example, and I decide, I have a certain client that also has to use SOAP, or that wants to use MQTT or gRPC, Google RPC. Then you start realizing, there's limitations to this approach. What I tend to do is I tend to have a service layer before the controllers, and then all that does is it handles the input and output for what is actually needed for that communication protocol. And then that way I can use the same controllers. So I can have a SOAP and a REST controller, one controller for both of those. Because at the end of the day, the logic is still not changing. I just have different ways to communicate with it. So that's the problem when you depend on these approaches, but we all do it. I do it. So this is a normal approach. But what we run into is, in this case, everything is contained within the application. So this is a typical monolithic application. You'll have your web front end. A lot of times people will go with a thin client. So the idea is, well, I'm going to go with a thin client because I want to have the same business logic for mobile apps and browsers. So if I keep all of the state on the server, then I can easily do that. So the difficulty is that if you want to make a change, so for example, let's say I want to make a change to a function, the clinic service. Well, I need to first go out to all these different controllers and make certain that that it will work for them. And some of these controllers may actually be other applications. And that's where you run into even more problems, is I make one little change in one place, I have to test all these other parts just to make certain that they didn't break. So the entire system, because it's so tightly coupled, is very fragile. Another problem is that we do a lot of tight coupling to a database. So for example, we have here some of the tables that were used in the previous slide. And let's say I want to change um, the specialties. Instead of having an integer, I decide I want to use a UUID, so I want a string. Then I would have to go to all of the applications that use that table, and this is where we run into a real problem with databases, is other applications, other systems will also be using this database, these same tables, because they find it convenient. So the tables start to take on a life of their own. And what happens is, okay, I want to make a change to a table. Well, I need to go talk to all the people. So I may have to have 10 applications, may have to go to production with me to make, and if any of them have a problem, we have to roll everything back. So it makes it very hard to test because now I made one little change to a table. I have to test 10 applications, so the company has to decide, do they want to pay for that? If not, well then probably I'll just end up making a whole new column that will have my table, my change, so I'll have multiple IDs that might be used because over time someone else decided, you know, I want a different ID. So these tables start to become hard to really change. And it gets to the point where if you make a change to a table, you don't know what other applications are going to break. So what we end up having in these monoliths is tight coupling from your browser and your mobile application is tightly coupled to the calls on a server, and then everything from the controller on down are tightly coupled to the database. So this is a problem. It ends up making it very hard to try and be agile. We'll be getting into that in a bit. So why do we have monoliths? Early on, we had mainframes, and it made sense that everything was monolithic because they didn't expect things to change fast. You were using punch cards. Everything was going to be going slow anyway. And they didn't have a lot of, you wouldn't have 2 or 3 mainframes that you could use because they're very expensive. So it just made sense. The problem is that modern applications have continued this, and a lot of it is because we look at how, like I said, how when you look at examples like GitHub, and you'll see in order to keep the tutorials simple, they'll just make a monolith. They don't want to make it more complex by starting to break everything up into parts and making it more manageable because they're trying to teach a tutorial. They're not trying to teach you how to design your application. And they're not going with the idea that this is the correct way to do it. They're trying to teach you how to use whatever it is that they are presenting. Unfortunately, we take what their tutorials show and say this is gospel. This is the way you're supposed to write your application. And so we continue to have these monolithic applications to this day. Problem, like I said, is we have long periods of testing. I remember one place I worked, when we got done with making changes to a customer service app, we had 3 weeks of testing we had to do because there was no separate QA. So we'd have this massive checklist. We'd split it up among the various team members, and we had to test to make sure that everything worked. And we had unit tests, so it was fairly frustrating. So you could make all kinds of changes, get everything into a staging environment quickly, but if it's going to take you 3 weeks to move everything into production after you're done coding, then you have a problem. You can't easily adjust because that means that if there was any bugs found, you either roll back or you fix it and then 3 weeks later you get the new version out. Nowadays that's bad. So during this time, we started having web services. We had Corba, we had SOAP, we had REST, we have MQTT, we have various RPC approaches. Lots of different ways to try and decouple the applications, the parts of the application. So the easy one to start with was just to separate the front end from the back end by making web service calls. In the beginning, we were using CGI calls, so they weren't web service yet. But those approaches still we carry forward to this day. This led us to a service-oriented architecture. So, for example, in this approach, you could see that they have a thick client and lots of thin clients. You have all these different services for performance reporting, for auto discovery. You still have one database. This is a fairly consistent approach. So you still have the tight coupling with the database. But in order to make this work really well, what companies started doing is we started having an enterprise service bus, an ESB. And ESB was kind of cool in the SOAP days because you have an order coming in. You need to see, does a credit card, will the payment work? Do I have enough inventory? So can I reserve? Can I pull it out of, make it unavailable so I can reserve it for myself? How do I, go through the delivery information? You have, taxes, all this stuff. So you have lots of information. So what you would do is you would go in, the data would come into the pipeline. You would be constantly transforming. So you would take what is in the pipeline, a part of it, you change it to be what's needed for the payment, for example, because the payment doesn't care about the actual how many things you're ordering, how many widgets. They want to know how much, so they can make the charge to your credit card. So you transform, you send it, it comes back, you enrich this packet, you keep everything moving along. So you have a pipeline. Fortunately, that ESBs are slow. XML can be very bloated, and service discovery is a challenge. We end up having lots and lots of web services inside our ESB, and you have to go and talk to the enterprise architects to figure out, or to the various teams to figure out, I want to do this kind of service. How would I use the function in the ESB? So it didn't work real well. Okay, so now we're going to be talking a lot. We were talking about databases and about coupling. There's different types of databases depending on needs. Most people are familiar with this area over here, where you have consistency and availability. So you can mostly, the database is always available. If the load is too high, you might end up not being able to make connections to the database, but as a general rule, it's available, and the database is always consistent. So if I have 3 databases, so I decide to go with having redundancy to help with load, they will always be consistent. Problem is that then that means that they can't be distributed. If you have distributed, then like this, then you either end up with these type of databases here, which is always available and distributed, or always consistent and distributed. as a general rule, I think that we're normally going to go with the idea of eventual consistency. Some of these I don't think are really truly consistent. They will eventually be consistent, but not right away. So if I insert a record, immediately pull, I may not get my change may not have been there yet, depending on which database I wrote to and which database I pulled from out of the various. So all out of my cluster of Mongo databases, I may have a problem. But this Brewer's theorem is critical for helping determine the correct database. So everyone wants to be agile. Early on, if you listen to Uncle Bob, companies took experienced people that they had trust in and they made them programmers. So this enabled people to. So I knew that I would do good work because my friend Joe works in inventory in the warehouse. If my program has a problem, it's going to make Joe's life more difficult. So I'm going to make sure and do a lot of good testing. I'm a expert on on that area because I've been working in it for a long time. So I'm an SME. I know what the needs are. Then we have modern programmers who just see their work as a job. They will do just the minimum testing to get by with what they need. What's become very popular nowadays is you'll see people using mocks, for example. So rather than actually going to a real system, they'll just mock it out and return back canned data. I also see a lot of people, rather than writing actual JUnit tests, for example, they will use Postman or SOAP UI. And they'll say, well, I did my testing. It's not reproducible. So, but that's the mindset. So the whole agile approach was to try and give developers disciplines that developers used to have, to try and make it more professional, and to try and improve, um, to make better code. Because at the end of the day, we have to ship. We have to have good quality code coming out. We have to meet the needs of the customers. So I try and tell people that Agile is really customer centered. So you think about it as I want to make certain that what's the best way to meet the needs of my customers? You want to have really good testing. You want to make certain that they were involved in helping to come up with the requirements so that their needs are met. And you have the right features coming out that will best help them. Okay, so we have this concept of everything is reactive. The word is overused. So, for example, you have reactive applications. Those are event-driven. That's RxJava, RxJS, um, Rx Kotlin, the reactive extensions created by Microsoft. Someone clicks a button, an event is sent out to the application saying this button was clicked, and then the various parts that care will get the response, consume the event, and they will do their part. So this is where we end up with futures and promises had come out. So you can have many reads and a single write. Because we're trying to make everything more asynchronous. I'm more familiar with the idea of streams of data. So for example, mouse movements, mouse clicks, those don't ever actually end in a real application, not counting login. So you're going to be clicking different parts of the application. You're going to be moving your mouse around. So you just treat these as a stream of events. You can then start to compose, so I can have different handlers. I can kind of pipeline them together, and I can create new ways to interact with the stream. You can also have, for example, if I change a variable, then that will ripple through the entire application. So that's what reactive applications are. Spring Reactive is also in this family. Then you have reactive systems or architectures. These are message driven. This is really the crux of what I'll be talking about. When you have the correct response is available when it's needed, then it's responsive. So if I click a button and have to wait 30 seconds for it to come back, it wasn't really when it was needed. I got impatient. I thought the application crashed. So I don't see it as responsive. But it depends on what it is you're trying to do. If I'm analyzing something from a telescope, I may expect it to take more time. So that's really based on the user's expectations about responsiveness. Now, if you're responsive under failure, because we work with computers, things fail. You have databases go down, servers go down, hard drives fail, networks get buggy. You want to make certain that your architecture can heal itself. It can recover and keep on functioning. If a database goes down, so I have to reboot my Tomcat server or my JBoss server because of the new database coming up, then it didn't heal. But so you want it to heal so it's resilient. Now, if it's responsive under load, so all of a sudden I have a lot of requests coming in on a certain part of my application, so I need to have lots of additional capacity. That's elasticity. Elasticity is great because it allows you to be more resource efficient, cost efficient, and friendly to the environment. So I don't have to, the old way is if I have to have 10 JBoss servers, I might only actually need to have one part of what I'm doing is where I need the redundancy. But you end up having to have lots of computers or lots of virtual machines just to try and handle the load. Then you have functional reactive programming, which I'm not really going to talk much about. It's largely reactive applications, but using functional approaches. So the key here is that messages are for communication and events represent facts. You can't really just, if I click a button, that button was clicked. What's the purpose of it? That will be based on the communication from the message. But I can save that click because that was a fact. Okay, so then we have the Lightbend, who at the time was called TypeSafe. They're largely behind Scala. They came out with this reactive manifesto. So for version 2, they made some minor wording changes largely. But the idea is that you want everything to be responsive. So that's the most important part. In order to do that, like we were saying, it has to be elastic and resilient. In order to make all of that happen, the only way that can work is it has to be message driven. The reason being because then you have very loose coupling. So for example, if I'm making client server calls and I stand up and I bring up new services to be elastic, then I will have to know that these new IP addresses are available, and then I can see about trying to work with them. So I'd go through an F5, I'd go through or some other load balancer. but I have to know, the system has to know more about it. It becomes additional complexity. Same idea with being resilient. If something went down and then I bring my the database up, it's not really going to self-heal if I had made static connections. The client would have to remake the request in order for everything to flow. So the best way for this to work is to be message based. So we send messages, we don't make REST calls, for example. So this is very difficult for some people. So now we're going to look at some approaches. Node.js is really popular. Node.js is one of the two approaches I'll look at that uses a reactor pattern. The reactor pattern is basically this, where you just have an event loop that just keeps going, and all you're going to do is you're going to take an event, you're going to find the handler, you're going to do something. You never want to do anything that's going to slow down this event loop. So anything that's going to be blocking or anything that's going to be CPU intensive, you would do in a handler, you would do it off of, not on the event loop. Difficulty with Node.js is because written in JavaScript, it's inherently single-threaded. If I have 6 cores, I'll have to have 6 Node.js servers, so that way they can all 6 cores can be used. It's going to be slower. Node.js can be good. It depends on what your use cases are. For microservices, Node.js can be good. For Reactive, you run into some issues. So, Node.js, comparing it to vert.x, you could see that vert.x is much faster, largely because it's compiled in Java. Even the vert.x in JavaScript is faster. And this is largely to a large extent, because vert.x also uses a reactor pattern, but they use 2 event loops for every core. So if you have 6 cores, they'll use 12 event loops. So they can process things much faster. Okay, so like I started with at the beginning, we had Spring. That was the very first example I used was Spring. Spring is immensely popular. It was really useful, in my opinion, in the J2EE days because J2EE was very heavy. You had all these different types of beans. You had a lot of overhead. It was a lot of work to try and design a J2EE application. Spring was much lighter weight. It introduced the world, made it more popular to use aspect-oriented programming. With Aspect-J was an awesome library. Then it becomes part of Spring. More people are doing dependency injection, so then dependency injection becomes more commonly acceptable. Spring was really good. Spring is trying to stay relevant, so now we have Spring Boot. When I did some work with Scala, I was using a library called Scalatra, and I would have Jetty would be embedded in my application. So I would just run my application, and it would come up with this very minimal web server. That's what Spring Boot does too. So if I want to try and be more reactive with Spring Boot, I have to have a lot of different applications up. So for example, I have a customer service application. I decided I needed to launch several of them. Well, then they will have to register with the service discovery system. So that way, the gateway, when it's looking at, okay, I need to forward on this to a customer service this information. It'll go as discovery. It'll ask Eureka, can you give me a microservice that meets these needs? It'll be given an IP address, the gateway will call it, all is good. If we have now things slowed down, so I can take down some of the customer service containers, they will deregister with the service discovery, the gateway won't be calling them anymore. So you end up having to have extra applications just to make everything work with Spring Boot, because it's largely just very focused on being an embedded application. Okay, so then we have vert.x. vert.x supports lots of languages. It was designed from the very beginning to be distributed. One way you can tell that is that it actually comes with its own internal service discovery and service bus. This becomes important because I don't have to have extra applications to make this work. It will work with other applications, but I don't need them to have my system work and to be reactive. So I can pass messages around through this service bus. I have circuit breaker patterns, so if something is going really slow, it will time out and I'll know that. And all I have to do is add them to my Gradle file. The correct line, I get this capability built in. vert.x is based on the idea of, they call them verticals. You basically, every part of your application is an executable. They all have a way to, you actually run them. And so they're all like lots of little standalone applications. So for example, here's one architecture. So you'll have your different, you might end up having in production at one point 5 different user account service containers. Depending on needs, generally what you end up doing is you end up having a database tied to each service has its own database. The reason you do this is because I want to make certain that if this database fails, I don't want to bring everything down. Or what happens if someone's doing a long-running query and they slow down a database? I don't want to slow down my application just because the database is slow. I've seen this a lot when during odd hours the database is being backed up. Then it will slow down the database and your entire application slows down. So, but then you run into issues of, well, then how do I do writes, for example? With web service calls, we tend to have, with REST, we have get, which is read, put, post, and delete are all writable verbs. So what you end up doing is, what I find useful is I'll have, for example, one user account service that is able to write to the database. And so it will connect to a database that is updatable. All the other user account services will have a read-only database. So I will connect, I'll do my update, I will put a message on the message bus to say this is the event that I did, and then all of the other user account service instances can get that event and they can update themselves appropriately. I don't necessarily want to use MySQL everywhere, because if I'm read-only, then why use a relational database? I might find it better to use a Mongo database or Elasticsearch or some internal cache. Redis, it doesn't really matter. There's lots of different types of databases I can use. So, and by sending the event, then I'm not tied to I'm not saying, well, you have to, here's the query that you're going to use. So they may use different keys. This becomes an issue, and now we get away from the idea of having a primary key that will be universally the same. So I can't say that for this particular user that their internal key is 27, and in every database they're always going to be 27, because it depends on when things, if all of a sudden I need to have more inventory services, then when I bring one up, I need to then synchronize that new database with the current databases to get everything to be consistent. So it might be a few minutes before it's actually ready to be used. Who's to say what order things were actually came in or processed to ensure that all these keys are the same? So, but this is the basic idea with vert.x, is just to have, you have your gateway coming in, you have, it will find out from the service discovery which, where to actually send the data to, it does its work, we move on. You can also have interaction between components, so they can either communicate on the event bus using RPC, or they can do a REST call to each other. It depends on the needs of on the requirements as to which way would probably be best. But either way is available. Really, the best way to do reactive, I think, is actors. I like Elixir because it's built on Erlang. We'll be talking about Erlang in a moment, but Erlang is the best. They've been doing reactive for 30 years. They know how to do it. Akka is a great tool. So you have for .NET and for Java. For the JVM, you have an Akka library. So instead of having these verticals, you would have each actor is a computational unit. So I don't necessarily make method calls. I pass messages to actors. And that actor is fully self-contained. It doesn't have anything global because it may not even be on the same machine, in the same cluster. It may not even be in the same data center. You could have one actor could be on the East Coast, and it could pass something to an actor on the West Coast. We don't necessarily know where these actors are. That's one of the beauties of this approach, because then you're fully utilizing your data centers. If one data center goes down, then now the system will automatically just use the data centers up. It's a very nice system, but it's much harder to learn than vert.x. vert.x is more of how we're used to doing things. So I tend to think that people should start with vert.x instead of Akka, mainly because if you're a startup, then you could go with, well, we'll just use actors. And people go in with that expectation that you're going to do something more cutting edge. So, like I said, the original reactive language was Erlang. The cell phone towers that you use are probably still running on Erlang. Erlang doesn't, they don't actually catch exceptions and return back messages, they just fail. They have the supervisors that monitor what's going on, and they will see, oh, there was a failure. You can have different logic and say, well, I'll try again because maybe there was a problem. They just do everything with messages. They have a distributed database built in. I think it's called Amnesia. Amnesia. Um, and Elixir is built on top of Erlang, which why I think Elixir is probably the best language for using for reactive services. Okay, so now we want to decompose a monolith. This is very difficult, mainly because you don't want to overload people with too many new terms too soon. So it takes a lot of upfront work, which is odd for me because I'm more of a hacker. Having come from a C background, I'm used to just, oh, you have a requirements? Let me just start typing it out. Let me just start writing it. With microservices, you can't do that. So first, what I tend to do is I'll group things by domains. So for example, you saw earlier you'd have like your user domain, you have a order domain, inventory domain. So you have these different domains, largely because some of the data classes will be similar. Odds are the user domain isn't going to be using inventory objects in its work. So you first figure out your domains. Take all the web services and just group them under the domains. So that way you can start looking at what you really have. And then create sequence diagrams for each service. Now this becomes difficult because this implies that you either have good requirements already or that the code that the monolith you're looking at was written well enough to where you can figure out what's a reasonable sequence. What's the flowchart look like? How should the data flow? It's not always the case. So you may end up having to do this step later, the sequence diagrams. Because a lot of times the monoliths, people will say, well, I'll be at the controller, and then I'm just going to go right to the repository. I'm going to skip the service layer, for example, because it's more convenient. So you end up having, it's not quite spaghetti code, but someone referred to one time as a ball of mud. It becomes very messy. It's hard to read. Okay, so once you figure out your domains, you need to figure out what type of database. And so you go look at the Brewer's theorem slide, and you start figuring out which type of database do you want for each domain. And then for certain web services, we'll need, so for example, if you need to do updates, you're going to have a different web server, a different database requirement than for all the read-only ones. But that also depends on, are you doing 90% reads and 10% writes, or is it reversed? If it's reversed, then you're probably not going to want to have everything go through one separate database that's writable. So you end up having different approaches depending on the requirements. But then you get into something that we don't tend to think about too much in acceptance criteria, failure cases. A lot of acceptance criteria see our happy path. As a user, when I do these steps, I expect to see this happen. Now we have to look at more about what happens when there's different failures. How often should I retry? How long do I wait before I time out? Do I want to wait 5 seconds? Probably not in some cases, because the user gets impatient if it's more than half a second. So I may end up having a much shorter timeouts. This is where the sequence diagram becomes really handy because you can start adding up all the timeouts and see how long could it, worst case, how long will the user have to wait. So you also have an API gateway, and you saw that in the earlier slide on vert.x. So the gateway is really just, they're going to do the basic load balancing. They're going to be doing heartbeat checks to make certain that all of the services are up. They're going to handle any failures. They're going to take care of authentication. They're kind of just the gatekeeper to the entire system. What I find handy to do is actually, I want to send JSON, for example, to my browser, to the web application, because it's going to JavaScript. JSON is native to JavaScript. It's a natural format for it to use, so I can do it very quickly. But to my Android clients, JSON is a foreign language. It takes more to parse. It's bigger. So you can use something like gRPC instead. And so you end up having, I want to just have one set of microservices. So before the gateway, between the gateway and the client, I'll have a thin gateway, a thin kind of gateway. All it's really going to do is it's going to know how to marshal and unmarshal the request and give it to the gateway in a known format. So I find that to be handy. So some of the challenges. Data is important. So often when we're trying to design microservices, we tend to forget that at the end of the day, it has to be stored somewhere. So you make certain you have the right database. DevOps is hugely important. Part of the reason we're going to microservices, we want to be able to roll out changes very fast. So you have to make sure that you're doing TDD and BDD. I like behavioral driven design mainly because it reads more like English. I could show it to the management, and I could say, okay, so when these events happen in this context, this is what I expect it should be the response. And they can read it and they can understand it. It doesn't take a lot of technical knowledge to be able to make sense of what these tests actually look like. A lot of times they're very similar to, given this context, when this event happens, then this should be the outcome. And you can have multiples of those. So you set up your context in different ways. As this role, the infrastructure already set up this way, then see what happens. Asynchronous design is hard. We like the idea of everything happening in sequence. If I know that I need to get information from multiple microservices before I can make a decision, I don't necessarily know when they're going to come in, so I don't know the order, so I'll have to do everything in parallel, have it come back, figure out when I get all the data, then figure out what's going to happen and make my next decision. It becomes very hard to try and think in an asynchronous way. That's a high hurdle for a lot of people. And then you also want to make certain your gateway itself is reactive. You want to make certain that it can scale horizontally. If I have a very popular program at one point and a lot of requests coming in, it would be annoying if some of those requests got rejected because the gateway was too busy. So it needs to be scalable. So my primary concern about Spring and Node.js is that they'll become distributed monoliths. Under pressure, people tend to write code the way that they always have. So I'll sit there and say, I'm already going to a database. But why should I don't want to have all these different little databases. So for this domain, I'll just have one database, and we'll just all use this Postgres database for the entire domain. So if I have 20 microservices, they'll all just use the same database. It becomes very easy to make them into little monoliths. That's why I call them distributed monoliths. And that makes everything worse than what we had before. So then if you find that you have a lot of distributed monoliths, a company will say, we're better off just having one monolith. So all that work we were doing was a waste of time. Let's just make one monolith. That's my main problem with Spring and Node.js is you haven't changed the way people think about software. They're taking their old approaches and they're continuing to use them and try and use them in a new way. But under pressure, they'll revert to their old way of thinking, their old way of solving problems. They'll go back to monoliths because it's what they're used to. Generally, if I'm going to try and do something with a new way, a new paradigm, I'd like to have new tools, new something that will push them out of their comfort zone and say, we can't go back to the old way. So let's make certain we don't do that. Remember that your microservices are part of a larger application. Your supply chain application may have many different parts to it. It might have artificial intelligence, it might have blockchains, it might have microservices from 12 different 12 different departments. So everything has to work together. So one of the issues is you want to know how long are you spending in each stage. So for example, if I know that this team, whenever I go to their code, it takes me longer, then I may need to go talk to them and say, okay, well, I'm spending 80% of my time in the services I'm doing that you're in control of. Can we look at why it's so slow? And what you actually want to give them, you want to give them the events. You don't want to sit there and say, well, this is what I passed to them, because that may be of minimal use. You want to say, here's the events that I passed to you. Here's the messages that I passed to you. Because then they can use that and they can, it's easier for them to troubleshoot. I think it's important to save events. So any updates I do to my, change I do to my database, those events should be saved somewhere in a write once, read many database, worm database. And then I don't tend to, for the databases, I don't tend to save gets, reads, because I haven't changed the database. It's kind of pointless. But I do, everything that comes in from the gateway should be archived, all those events. So that way you could say, well, how often are we really doing reads, gets, and you can get better numbers. You can do more analytics on these. And part of what you should be saving, though, is also how much time is spent in every stage. What was the result? You want to know, I had 3 failures here. When I make this particular type of call, it goes into this microservice, and I tend to have 2 or 3 failures. It might be worthwhile to look into that. You may want to use Kafka to help communicate between external systems so that you're still doing everything message-based. And then you can use Kafka Connect, for example, to do communication. So reactive microservices are hard to design. You can't just cowboy it. You actually have to do a lot of upfront work first. A lot of thinking, a lot of looking at, well, what's going to happen when something goes wrong? I personally like the keep it simple approach. If you find that you're having to add a lot of different applications, like the Netflix stack, then you may want to rethink your approach, because then that means that if I have all these extra applications, then I have to make sure that they're redundant, that my infrastructure team knows how to use them, knows how to troubleshoot them. It's just lots of additional complexity. Ensure your events are captured, because then, like I said, you can replay them, you can debug with them. One of the problems I have is it's a pain to debug these applications because I can't just put a breakpoint in. I like don't put breakpoints in, and then when the code gets there, it stops, and I can look at what's happening. But if I do everything as Docker containers. So just because I put a breakpoint in my IDE, it's not actually running it. You can do that if you know which events you're going to be getting. You can write your unit tests and you can actually run everything in the IDE. I just find that integration tests become really important here. But it's harder to troubleshoot. It's harder to debug. So that's basically the introduction to microservices. I'm going to be doing some additional presentations to go into more detail about the different parts. I don't tend to focus a lot on terminology. So for example, if I'm sitting there and I'm saying, okay, well, I'm not going to add new web services to my monolith. I'll create new microservices, and then we'll slowly start to migrate the web services into a microservice. Someone pointed out that's a strangler pattern. I don't really care about terminology, about, well, this is what the word of the day is for this how you describe it. I tend to just look at, is it reactive? So if someone gives me a solution, I say, okay, well, is it elastic? Is it message-based? And that's what I focus on. The database part will always be, I think, the biggest sticking point, though, because it's a hard sell to businesses to say, to management to say, I'm going to need to have redundancy here, and so I'm actually going to have them inside my Docker containers. But they're not always going to be consistent. So you need to figure out how long could it take when I do a create, and then I want to get the information from a different instance. How long should it take for this to happen? It's a hard sell. There's a lot. I think that's the hardest part with reactive, is it's very different way of thinking, and so you want to keep it simple. So introduce new changes as once you get comfortable with the first approach, then add more. So what you'll end up finding out is that by the time you get done with your application, with your migration, the very last microservice you did may be in a different language. It may have a lot of different capability than the very first one, and that's fine. You can go back, and as you need to, you can go fix the earlier ones. But that's one of the benefits of this approach is not everything has to be in the same language. They don't all have to be using the same technology stack. What is the best approach for each, for that particular set of requirements? And then that's what you use. So have a great day, and I'll talk to everyone. I'll respond to any questions that people have. Bye-bye.